Hi everybody, Timothy Ferris here, coming to you from quarantine to talk about finding life beyond Earth. The question that's been put to us is how and when extraterrestrial life might first be detected, and I have to confess I don't think I'm going to be of much help on that question because I don't know the answer. As to how we might detect extraterrestrial life, fortunately our species continues to become increasingly sensitive to what's going on out there. And also we're sending probes to study planets here in the solar system. So we might find life close to home, perhaps deep under the surface of Mars or in the oceans of one of the Jovian satellites. Or perhaps we're going to find it on some other system as by taking the spectra of a planet as it passes in front of its star from our perspective, so that that starlight goes through the atmosphere and you can perhaps detect traces of life that way. As to when, I don't know when we might find life beyond Earth, but I've read that most people tend to underestimate the amount of change that will take place in the next 20 years and overestimate how much will take place in the next 10. So to hedge my bets, I'll estimate that we'll find signs of extraterrestrial life sometime more than 10 years from now and less than 20. It's not that I don't think that there's lots of life out there. Actually, I think life is cosmically abundant. And let's go over a few of the reasons, the arguments that are often made for the prevalence of extraterrestrial life. First, just the odds. Our galaxy contains something like 400 billion planets, so that even if life is rare, even if it only occurs in 1 in a million cases, that would still be millions and millions of planets. 400 billion planets is a big number. If you had an encyclopedia that had one page devoted to each of those planets, and all you did was page through that encyclopedia at a rate of 1 page per second, day and night, just to glimpse each of the planets in our one galaxy would take you 12,000 years. That's one of the features of the universe. The universe as a whole may be infinite or finite, and we don't really know, but the universe is phenomenologically infinite from the standpoint of any observer. That is to say that any random observer, such as ourselves, will find that no matter how much they investigate the universe and how much knowledge they accumulate, it will still be only a tiny fraction, perhaps an infinitesimal fraction, of the whole. So it's one of the great things about the universe is that we have a lot to learn. We always will have, and that's true of anyone else who lives here too. It's a big place, and there are lots of experiments going on lots of planets. The second is the argument from naturalness. This is simply that life here on Earth appeared quite early, just about as soon as it could on the violent young planet. And that suggests that at least for planets with environments like that of Earth, it is a natural thing for life to emerge. Sometimes there's a tendency of people to say, well, a planet can't have life unless I'd be comfortable there. It's worth keeping in mind that the early Earth, when life appeared here, would have been lethal to human beings. If you or I went back there in a time machine, it would kill us, in part because there was no oxygen yet in the atmosphere for us to breathe. So life on Earth appeared early, and having appeared, it has survived ever since. So survival is another argument for the prevalence of life. I think perhaps it was a mistake for environmentalists in the 1970s to talk about life on Earth as if it were fragile. Individual species might be fragile. Our species may turn out to have been fragile. But life as a whole is tough. It is found on Earth from the highest reaches of the atmosphere to as deep inside the Earth as anyone has been able to dig. It's found in hot environments and cold environments. So once it gets started, the odds are, it seems from Earth, that it will survive. Now you have to be careful about bias effects here, because had life on Earth not survived, we wouldn't be here to look back and talk about how tough it is. But its variety and the fact that it thrives in so many different environments suggests that life can do fine on many sorts of other planets. And finally, what might be called cosmic complexity. The fact that nature, in the nature of nature, produces complex systems. Let's look a little more closely at how nature builds complex systems. This wasn't so obvious in the early days of science, when the things that were discovered initially were regularities, cause and effect events, and from that framework, the appearance of life looks miraculous. But as more has been learned about nature, particularly on the quantum level, we can see that nature will build complexity wherever the environment permits. Nature and science work the same way. They're constantly running experiments and ruthlessly discarding everything that doesn't work. So if we look at the early universe, let's freeze time, let's say at 380,000 years after time zero, when the so-called Big Bang was occurring. If we could somehow put ourselves in that environment, we'd find that it was extremely hot, energetic. Let's say we took samples. Somehow we went around in our hazmat suits in this extremely hot environment, and we took 10 buckets of the universe at 10 different locations. We went back to our parallel universe and did double-blind experiments. What we would find is that the contents of all those buckets was identical. Each bucket contained lots of high-energy fields, some nuclei of hydrogen atoms, a little helium. But the important thing would be that it's the same everywhere. The early universe was undifferentiated. Today, if you did the same experiment, let's say you did in our part of the universe, one of those buckets might be space. Another one might be some dirt with living things in it. Seawater, also full of living things. Some pages of Shakespeare. In other words, in at least parts of the universe, nature has become much more diversified than it was before, and this is a natural process. The most diversified system known to humans is life, and the most complex system that we've ever encountered is the human brain. The tendency of nature to build complexity is so pronounced that even writers like Jorge Luis Borges note that, in his words, each thing implies the universe whose most obvious trait is complexity. Let's take a closer look at how it comes to be that we live in a world in which everything around us is some kind of a structure that has managed to endure. If we look at a chaotic system, such as that fiery environment back at 380,000 years after the beginning of time, it's chaotic, but chaotic systems, by definition, cannot avoid occasionally, here and there, producing areas of relative order. It's mathematically impossible for a chaotic system not to produce some degree of order. I like to call these ordered areas structures. Whether a given structure endures, or you could say how long it endures, is determined by two things. First, its internal integrity. Does it make mathematical sense? Quantum systems compute this all the time. They're constantly looking at futures, at their own futures, and canceling out those which do not have internal integrity. And secondly, its environment. So any complexity that appears in the universe will endure or not, depending upon its internal integrity and the environment in which it finds itself. Now, the interesting thing is that enduring structures, such as our solar system, produce their own environments, and further innovations can emerge in those environments because they're different from the more hostile environment in which the earlier systems may have emerged. We've become familiar with this because that's how Darwinian evolution works. That's how life got going. And in my view, a great many other aspects of nature work in exactly the same way, and Darwinian evolution happens to be the way we first encountered it. The prospect of extraterrestrial intelligence is particularly interesting because, of course, of its complexity and the ability of an intelligent species to create new, innovative, and more complex systems in turn, to accelerate a process that's been going on in nature for a long time. From the standpoint of looking for extraterrestrial life, the extraterrestrial intelligence that we would be able to detect, any such intelligence, would have to have language, otherwise it can't communicate, and technology, because otherwise it can't communicate across interstellar distances. This is why we generally think of us humans as having come on the scene pretty recently, as being newbies on the cosmic scene. The Milky Way galaxy is more than 10 billion years old, and yet we've just shown up in this interstellar game. We've had language for only about 100,000 years, and we've had technology that can be detected at interstellar distances for only about 100 years. So we're just getting started in this, and I'd be surprised if there hadn't been intelligent life in the galaxy before we got here. Let's look briefly at two major objections that have been raised to the hypothesis that there is intelligent life elsewhere in our galaxy. The first consists of post hoc estimates of the probability of intelligence emerging. These arguments consist essentially of looking at the history of life on Earth and the emergence of human intelligence and language, about which we don't know very much, and trying to calculate the odds. Basically, you calculate the odds of each step and then you multiply them together, and what you find is that the emergence of intelligence appears to be very rare, so rare that maybe we would be the only intelligent species in the galaxy. The problem with these arguments is that it's very difficult to really assess the probabilities, and then when you multiply them together, any errors you've made increase. That's the post hoc issue. If, for instance, we were to calculate every little thing that's happened in your life and that's happened in my life that led to my saying this sentence and you're now hearing this sentence, we might well calculate that it's virtually impossible for such a thing to have occurred. But of course, here we are, and these seemingly impossible things occur all the time. So the difficulty with post hoc is we only have one sample of life and only one sample of intelligence, which we're defining as having language and technology. So it's hard to estimate what the chances are that these things would have emerged somewhere else. They're not necessarily wrong arguments, they're just difficult to assess for the same reason that they're difficult to construct. The other argument that everyone's heard of is Fermi's paradox. It's not really a paradox, and it's not really any work of Enrico Fermi's. It's just that Fermi was a great physicist and a great skeptic about people's ideas. And one day when some of his colleagues started talking about extraterrestrial intelligence, Fermi said, well, where are they? That is to say, if they're smart creatures out there, why haven't they come to visit? Now, I find that in discussions of extraterrestrial civilizations, intelligence elsewhere, people tend to neglect the dimension of time, and that's the difficulty with Fermi's argument. I'll just read you something here that's adapted from the liner notes I wrote to the release of the Voyager Golden Record, because it bears on this question. Obviously, if there were never any intelligent civilizations out there, and never will be, then there's not much point in our sending a specimen of our culture into space to drift among the stars of our galaxies for billions of years. If spacefaring aliens visited Earth for, say, a year at some random point in the past, the likelihood that we today would know of it is the age of the Earth divided by the 100,000 years during which humans have had language. Because if, an alien starship landed and they planted the flag and they spent a year here studying Earth, and early humans were gaping at them from hidden behind trees, they would have to be able to tell other humans what happened and to tell their children, their grandchildren, so that we would have at least some kind of legend about this. There are some legends like that, but they don't survive the test of did they see anything that they wouldn't have had in their own culture at the time. So the odds of that having happened, that if a spacefaring civilization landing during the last 100,000 years, is 1 in 45,000. Therefore, even if 100 different expeditions had come to Earth in its more than 4 billion year history. And they'd all planted flags and put up monuments and studied the Earth and then gone on to reconnoiter another planet. The odds that we'd have heard about any of those visits is still under 1%. This slide is adapted from a film we made called Life Beyond Earth. And it bears on the question of time, specifically how long do intelligent civilizations typically last. So we imagined this in terms of each civilization being like a bulb on a Christmas tree. If each bulb, as it goes on, represents the appearance of a new civilization in our galaxy. We have no idea how many there have been in the 10 billion year history of our galaxy, but it's some number. Maybe it's one. I think it's probably a higher number. And the question then is, how long does that bulb stay on? How long does the civilization survive? If they survive for long periods of time, then the situation today looks like the tree on the left. There'd be lots of them, and our chances of detecting one accordingly are higher, simply because the distance to the nearest one would be much less. On the other hand, if civilizations typically arise and then disappear in some short period of time, say 100,000 years or maybe 1,000,000 years, then you get a Christmas tree more like the one on the right, where any given observer emerging into technological maturity, as we're doing now, and looking around, will find that it's a long way to the next civilization, and therefore they're harder to detect. If you look at stars, you know, most of the stars in our galaxy are dim dwarf stars that were born early in the galaxy's history, and they last a long time. They've been shining dimly for billions of years, and they're going to last for billions of more years. Also in the galaxy, and these are the stars that you may mostly make the constellations out of, are these supergiant and giant stars. They make an impression, but they don't last nearly as long. So the question is, are extraterrestrial civilizations typically more like dwarf stars? Once they get started, they endure. Or are they more like giant stars that make a big splash and then go away? When you consider the long history of our galaxy, and if we assume that civilizations emerged at some rate, some unknown rate, for much of that history, then it begins to seem more likely that we would detect the artifact of a civilization that used to exist or might still exist, but had built a lot of things, than that we would hear from or be in touch with a planet where a government or an amateur ham radio group was broadcasting a beacon that we happened to pick up. Such beacons are expensive, and I'm not sure that any civilization will want to keep broadcasting them for millions of years. So it might be that our first sign of intelligence beyond Earth consists of an artifact such as a Dyson sphere built around a star, which might or might not still be inhabited. Interplanetary scale engineering, the spillover from radio or laser communications, things of that sort. And I'd like to end here by talking about one possibility, which is the networking of interstellar communications by advanced civilizations. I'd just like to discuss here for a moment an idea that I originally published back in 1975. There wasn't any internet then, so it was harder to describe. Today I would call it a galactic internet, and that term is being more widely used now. And the idea here is that if you are an advanced civilization at any time in the history of our galaxy, that there is some significant number of other such civilizations, at 10 or 100 or whatever, you would find it inefficient to maintain communications individually with planets of these different civilizations across the galaxy. You'd be better advised to invest in building a network. One way you could do this is self-replicating probes, an old idea. A civilization launches, say, 10 probes, each very small in mass, but very smart and capable of a lot. At a low velocity, let's say a tenth that of light, to 10 other planets and planetary systems. When these probes arrive, they set up housekeeping on, let's say, an asteroid. They establish a communications link back to home and also with the other probes. And most importantly, in the fullness of time, they build 10 more probes and send them on to 10 other planets. If you do this, you can construct a communications and reconnaissance network that's reporting to you on other planetary systems of interest and taking care of your communications needs over an expanding part of the galaxy. You could have such a network of 1 billion star systems within only 100,000 years. So for a small investment, you get a big return. And what constructing a network of this kind does is really a few things. First, of course, it provides more efficient communications among civilizations. Every civilization that connects with it can then communicate with every other civilization that happens to exist at its time. If there's never any overlap of such civilizations, then it's unlikely anyone would build this system. It has an archival function in that civilizations can put their histories or art or science, whatever they want to brag about, on the internet and subsequently be available to everyone else, including civilizations that hadn't appeared yet. It's accessible, and this is important for planets like us who are just getting in the game, because if there's a galactic internet, then the chances are that a node of it will be much closer to where we are or any other emerging civilization is than if we have to rely only on making contact with civilizations that A, currently exist, and B, are interested in looking for emergence, peoples like ourselves. And finally, the internet would have to be secure, allowing newbies to log on without revealing their presence in case they're worried about what might be out there. Now, I don't know whether we have a galactic internet or not, or whether we'll first make contact with some kind of biological species or with a machine intelligence operating an internet or some other kind of a system. There are enough prospects to keep science fiction writers in business for forever. And it's because of all these variables that I can't say with any assurance when and how we might detect evidence of life elsewhere. But the evidence does suggest that this is not a pipe dream. It is not, as it used to appear, to be something that runs contrary to deterministic science. The existence of life and perhaps of intelligence appears to be a normal outcome in a universe that constantly produces diversity, constantly experiments, and has, in fact, already produced life and intelligence. So I don't think that happened only here, and it certainly hasn't happened, I think, only once anywhere. So all the questions involved in looking for life elsewhere have to do with quantities, like how long will we have to search to find it? How far away will life be? How rare is intelligence as a fraction of life? Those are answerable questions. As long as we keep investigating the subject, we have a good chance of finding those answers. Thank you for listening.